the UR5 manipulator, which is over here. UR5. So you can go here and then download the files, and okay, so here is you don't see a download. Usually you should see a download, right? And then you don't want to download each file. Like you could do this, and then I think that will let you download. You can click on this download raw file, but then you'll have to do that for every single of these files. It's just time consuming. So there is actually a way to do this. If you search for download GitHub directory, there is this website, just download directory.github.io. So you can take this and then copy paste it here. And then enter, and then it actually downloads the files for you, and then it will actually download it in your downloads folder. Then you can unzip it and use it. So remember, that's super easy to do. But if you didn't know this, then it just becomes kind of hard to download the files. Okay, so I got those files, and they are over here. The UR5 XML is there. Let me just open that one. It's actually opened here. There's another one which I want you to open, and this is how MuJoCo Manager does it. It's called a scene.xml. Okay, so the scene.xml actually includes the UR5. So you need to really open scene.xml, because then that will open the UR5. The scene.xml actually has some visuals. It defines the floor, and then that's about it. So the first object is the floor, and then it calls this, and everything else follows. So if you go to terminal here and then type Python -m MuJoCo viewer, the viewer opens up. I have it already opened. What you want to do here is drop the scene.xml and not the UR5. You could drop the UR5. So let's say if you want to drop UR5, you'll see that it shows up without the visual and then the floor. And then you probably want to drop the scene so it looks a little bit better, right? Okay, so that's the manipulator. If you want more details of the manipulator, what you can do is you can go to rendering, and actually let's see the joints. So it's really hard to see the joints. So what I did was I did a slight modification to the scene files, sorry, the XML file. Okay, right here, they have defined, this is what was downloaded. What I did was I actually made a slight modification here. I'll comment this out. Okay, the comment is this way. And then uncomment this part. Okay, and then you can try reloading this. So let's go here and then reload. All it does, it makes the object transparent. So what I did was, if you look at the opacity, the only difference between these two is that I changed this from 1, the RGBA value from 1, which is opaque, to transparent, so 0.2. If you do 0, then you will not see any manipulator. So this actually helps us to visualize. So if you see, these are the joints. Let's see if I can rotate this. Nope. Okay, there it is. Alt will help you rotate. Alt and move the keyboard. So these are the joints. The end effector I've shown with the red dot, that was, I think it may not have been the way it is in the downloaded files. I had to manually change that, but you can look at that in my code. The other thing you want to do is perhaps to look at the frames, which I think is important. So the world frame is right there at the base. RGB is XYZ. And then if you want to look at the body frame, you'll see something like this. You can count these 1, 2, 3, 4, 5, 6, 7. If you look at the joints, I'm going to drop this. It's a bit hard to see, I think. Yeah, so maybe it's okay. There's 1, 2. There's one. See if you can. It's one there. And then one there. So 1, 2, 3, 4, 5, 6. So there are 6 joints, but there are 7 frames. And as I said last time, one of the frames is the base frame that does not have a joint, and that will be obvious when I show you the UR5 XML. So let's close this, and let me just go back and put this back. The comment and then uncomment this part. Okay, so let's just, I just took the XML, UR5 XML, and I copy pasted parts of this in the doc so we can talk about it. But essentially, there's a default part, and that basically defines some default properties for the manipulator. For example, an example is joint axis. If you don't specify a joint axis for a joint, then it'll actually use 0, 1, 0. It'll use this range. So that range is minus 2 pi to plus 2 pi. So all the way full circle, right? And then if you use joint limiter, it'll use minus pi to plus pi, 180 degrees only, so half of the circle. And then there are other things. We'll talk about it in just a bit. Don't worry too much about the mesh files. This is where the manipulator is actually defined, the properties of the manipulator. And we'll go through them one at a time, okay? So all this, I copy pasted in the doc file, and then we'll talk about this. So here is what I did is you just go through this instead of trying to go through that, but you can go back to the XML and then look at it through the viewer. Okay, so that's the manipulator for you. The red dot, I created that by putting the sphere of a certain size, otherwise it's not visible. This one just shows the world frame. So let me write this down. This is the world frame. Okay, so the frame is fixed, it does not move. In order to make this possible, I made it transparent, as you can see. Then I showed you there were joints. In fact, there are 6 joints. The blue arrows indicates the direction. And if you want to know what direction they are, you can look at this and look at it in conjunction with this. So RGB is like this. So you will go here and then just draw R. So RGB, right? And that's how you'll figure out the axis. So for example, this one, you need a white. So for example, this one, you can see it's pointing up. The way you'll define this would be 0, 0, 1, right? Based on this P is Z. Then if you look at the body frames, as I said, there are 7 frames. But only 6 joints. Okay, so why is that? It turns out that this frame, this one, is the base frame. It actually doesn't have a joint, and I'll show you how that comes up in the XML file. They define that because this manipulator sometimes is mounted on a mobile manipulator which moves, and I guess there's a fixture for the manipulator to be mounted, and that's why they have that link which doesn't have a joint. Okay, so 7 frames, but only 6 joints. Okay, let's move on to the properties. I just copy pasted this from that file. We'll come back to this as I proceed in explaining the different parts of the XML. So base length, as I said, is this one. It does not have a joint, and you can see it from here. You define a body, but you don't define no joint. There's no joint tag. That means there's no joint associated with it. Okay, so what is not very obvious is this part. This is a new thing. We've not done this before. What do you mean by specifying a quat over there? That quat, so one thing about the quaternion when it comes to rotations is that a quaternion has to be of magnitude 1. So if you square the individual terms and add them up, it'll come out to be 1. Now that one is square root of 2, so that is not quite what a quaternion should be. What MuJoCo does is actually, before it uses that quaternion, it normalizes the quaternion. So what it'll do is it will take this quaternion 1, 0, 0, 1, and then it'll normalize. So it'll be 1 divided by square root 2, 0, 0, 1 divided by square root 2. Okay, and then if you convert this to Euler, right, there is, we've seen how to do that. You'll see that the angle corresponding to this is 0, 0, 90 degrees. So it's rotation by 90 degrees about the z-axis. So what does that mean? Well, it's kind of obvious from, you need to look at the world frame. So if you look at the world frame, which I drew some time back, so this is the world frame, right? Copy. Okay, so this is the world frame. Okay, that's before the base frame. So that's the first frame, then comes the base link. So what that quaternion represents is how you need to rotate the base frame with respect to the world frame, that is the previous links, to arrive at its configuration. So this says that you need to rotate by 90 degrees about the z-axis. So take the world frame and then rotate the world frame by 90 degrees about the z-axis. So 90 degrees about z. So you'll see that the z-axis is unchanged, and then this r. So the way to do it is take your right hand, stick your thumb in the direction of B, and then curl your fingers. The finger's direction gives you the way you need to rotate. So the r will turn by 90 degrees, and it'll point this way, right? And then the green will go there. So that's what it means to have a quaternion here. It just shows how the body frame rotates. Okay, what else? Inertial mass, that's the mass. The position is right at 0, 0, 0. So this means that the center of mass is right at the origin of the body frame. Don't worry about the diagonal inertia. We'll come to that later. And then it tells you what mesh to use from the mesh which is provided by the manufacturer. Okay, let's move to the next link. The shoulder link is the next link. It is right, this one. Okay, so it's defined here. It is given a position. So this position is the location of where the body frame is with respect to the previous body frame, right? Remember that in our matrix, the R matrix, this O is precisely this. It's the position of the frame with respect to the previous frame. So in this case, I would just put 1 0 1 0. This should be 1. So that's that. So you see that it's 0.163 along the z-axis, and if you actually zoom in this, you'll see that this is actually mounted 0.1. It's along the z-axis. This distance is 0.163. Okay. Then there's the inertial mass position. This just indicates that the center of mass is right where the body frame is, right in that place. The diagonal inertia, we can skip that. It says the joint name is, you give it a name, it doesn't really matter. And then the axes are 0, 0, 1. So 0, 0, 1 means it's along the z-axis, the one and the last one. We can see it over here. If you, that's that, 0, 0, 1. Okay. There are other things which we'll skip. Collision and all, we'll not talk about that. It's too many things to take in one thing. We can get to the collisions later on. Okay, so next link, upper arm link. So now I think you kind of see what's happening with the XML. There is the link which you can show, which is going to be this one. Its position, you can see that's along the y-axis, so 0.138, and that's what it looks like, right? If you look at this figure, if you draw this distance, it is along the y-axis, 0.138. The quaternion basically says that how much you need to rotate it, and you can see that this is rotated about the y-axis. The green is unchanged, but then the blue is turned down. So you can convert this quaternion to an Euler angle, and I'll leave it to you as an exercise. Convert that to an Euler angle, and you see that it corresponds to 90 degrees rotation about the y-axis. Okay, then there's the inertial mass position, which the center of mass is. So it's not exactly at the body frame, but it is along the y-axis by this much distance. And this distance is going to be along this blue, okay? The blue which is over here, not the previous blue. Diagonal inertia, joint name, we'll forget the diagonal inertia. Now you can see the joint, interestingly, has been specified a name, but there's no sign of what direction that axis is. You can see that the axis from this figure is 0, 1, 0. So this axis is 0, 1, 0. So how does it understand that it is 0, 1, 0? Well, I told you there's a default configuration. So if you go to default, you'll see that if nothing is specified for the joint axis, it should take 0, 1, 0. So that's what default applies to. So the default is, it would be here. So this is 0, 1, 0, which is the default. Okay, and then the other things we'll skip. Forearm link, okay, which is this one. And then I'll let you figure this out yourself. We've done examples of quite a few examples now. This one actually uses the joint limited property. So if you go to, again, default, you'll see that there is a joint limited. It's right here. So this joint limited will have the same axis, 0, 1, 0, but it'll have a different range. So the range of motion is only 180 to minus 180 to plus 180. So it's full circle, but it is minus plus. Okay, so that's that. We go here. I'll just put here 0, 1, 0 is the axis. We'll skip the rest. Wrist one, just show it here. Wrist one, again, can go through this. Wrist two, which is this. Wrist three should be this. And then finally, we have actuators. Now, the actuators is as a separate tag. You can see here, it should end. And so what we're doing here is when we specify an actuator, there are different types of actuators. You could have an actuator which is like a servo. A servo is basically does position control. You can have an actuator which does force control or a torque control. most motors are, torque control, but or current control as they call it. But to make our life easy, we like to think that you command a position of 30 degrees and the manipulator just goes to 30 degrees. So you want to really define a servo, and we'll get to the details of how you convert a motor to a servo control when we get to control. But this actuator here is a position servo or position control. A position control is typically like this: minus Kp theta minus theta reference, we call that reference, minus Kd theta dot. This is a PD, what they call a proportional derivative control. Okay, so you can see that it's specified with this tag. It's called, well, it's this name, position, well, it uses this position class, position class. So where is this position class? Well, it's actually in the default properties. If you go back to the default properties, they have defined actuators, position, default class position. And then for the default class position, they have specified, in this case, a gain. So this is their Kp value, this is their Kv value. So all those joints will have this Kp and Kv. Now that's sometimes not ideal. You might want to have different Kp, Kv. So it turns out that Kp, Kv of these values, 2100, were used for, if you go back, you see that this position, but then it becomes position limited. So there's a difference here. Okay, so what's position limited? If you go back to the default properties, you see that there's position limited, and that basically means it has a different control range, but it uses the same gain. So the control range for just position was negative 2 pi to positive 2 pi, but position limited was this. So it uses the same gains, but it uses a different range of motion. And then if you go back here, you'll see that there's another one, which is position small. So position small, small, small. So what does that mean? If you go to default property, you'll see that this position small. This one actually uses a smaller gain. Was 2005 was the original one, but 500 for this, Kb small. And this actually corresponds to some of the smaller joints, the wrist joints. And if you use a high gain for them, they probably will go unstable. That's why they've used a smaller gain. So that's the actuators. And then finally, we at the end of the file, we look at the keyframe. So the keyframe is useful to initialize the actuator. So in this case, we specify the actuator should start with this particular angle. So remember, there are 6 joints, so 6 angles. So this will be theta 1, theta 2, so on till theta 6. And then when you press on load key, it actually shows those angles onto the manipulator, so you can start from any configuration. When you do that, remember, with an actuator, you can also specify the actuator to have, remember, actuator commands are position commands, and so CTRL will be the same as QPOS because we want the manipulator to stay at that position. Okay, so that's how the XML file is to be interpreted. Now